Namaste. Namaste everyone. Hope all of you are doing well. We will discuss about second PUC physics. Namaste. Hope you are doing well. Those portions which are left with after Corona lockdown holidays. The first part, right? Second part we have finished. Now the first part, magnetism and matter and EMI AC, 4 chapters, very important chapters. Last 2 chapters very important, then very easy also. So magnetism, we are in halfway, right? So let us remind the things what we have studied, right? One is Biot-Savart's law. So moving charges and magnetism, that chapter. What does Biot-Savart's law say? That gives a magnetic field due to a conductor, an element. The magnetic field due to an element is, okay, here, due to a small element of length dl. Please rewind it once. You take your notes book and just rewind it. Otherwise, the future classes will be very tough for you otherwise. So select a point here, and if the whole conductor is like this, a part of the conductor carries current like this, and if the current is in this direction and join this by a radius vector r, then you know that if you just clasp it with the right hand like this, the right hand clasp rule gives the magnetic field due to a current element. So clasp it with the right hand, the fingers show like this into the board. You know how to show the magnetic field into the board like this, and let theta be the angle made by the length of this conductor with this position vector. Then the magnetic field here dB is equal to mu naught by 4 pi I dl sin theta by r squared. But in mathematical form, actually this is dl cross r, right? dB is equal to mu naught by 4 pi. So I multiply and divide by r, then it becomes r cube I dl cross r divided by r cube. Otherwise I don't have a r here. Multiply and divide by r. So you can write dl cross r. dl is a vector now along with the current. That is called current element. So it has a direction. So if you do it like this, you will get the direction of magnetic field. So mu naught by 4 pi I dl cross r divided by r cube. A b sin theta. A b sin theta you have. dl r sin theta. Or you can write r cap also, which is so not r cap. R cap cannot be the answer because it is like this. Some b cap, something like this. Or better you write it like this well only. Okay, so that is a magnetic field due to a current element, a part of the conductor at a point P, say. And we know the force acting on a charged particle moving in a magnetic field, F. Okay, you keep this here only. Force acting on a charged particle moving in a magnetic field. Suppose there is a magnetic field like this of strength B, and if a charged particle is moving in a velocity v, making an angle theta with the direction of the magnetic field, then force acting on that is qvb sin theta. And this can be written as, of course I will use small letter q. Q is a scalar quantity, and v cross b like this, q into v cross b, vb sin theta. And when will the charged particle experience maximum force? When it moves at 90 degrees. So F maximum is qvb when theta is 90 degrees. So if a charged particle moves perpendicular to the magnetic field, it experiences maximum force. When the charged particle moves parallel to the magnetic field, it doesn't experience any force. And if a charged particle moves at some angle, of course force will be neither maximum and nor minimum. If the charged particle moves perpendicular to the magnetic field, then it experiences a centripetal force, because you can use the Fleming's left hand rule. The first 3 fingers of the left hand are stretched mutually perpendicular to each other, with 4 fingers showing the direction of magnetic field, middle finger showing the direction of current, then motion of charge, that is one and the same, motion of charge and current, and the thumb shows the direction of force. For example, here, if the charged particle moves perpendicular to the magnetic field like this is the magnetic field, and if the charged particle moves like this, stretch the first 3 fingers of the left hand, hold this the motion of the charged particle like this upwards, magnetic field is inside, force is magnetic field is forward, charged particle motion is upward, force will be shown inside. So it shows inside. What do you mean by that? As soon as the charged particle moves like this, and it will be carried inside the board, and it moves in the circular path like this. So if you imagine the magnetic field like this, and proton is moving like this, say a proton is moving like this, magnetic field is from left to right like this, proton is moving like this, then the force will be like this. So as soon as the charged particle proton enters into the magnetic field, it will be pushed up by the magnetic force, so it moves in the circular path. So when a charged particle moves perpendicular to the magnetic field, the same force acts like a centripetal force, and QVB at that moment turns into mv squared by r. What is mv squared by r? It is the centripetal force acting on the charged particle. It keeps the particle in the circular path, and this becomes the principle of cyclotron. A cyclotron is a device where we make the charged particle to move in a circular path, and radius of the circular path can be obtained from this, and velocity of the charged particle can be obtained, and so many things, a period of rotation, so all the things can be obtained. So a charged particle moving in a magnetic field perpendicular to the direction of magnetic field will encounter a circular path since the force is perpendicular to the direction of motion. Because here, if you observe, force is perpendicular to the direction of motion, and that makes the charged particle move in a circular path. Now you know, if the charged particle moves parallel to the magnetic field, its motion is a straight line, because no force acts on it. No force will divert its direction. And remember, magnetic field only changes the direction. It doesn't change the velocity or speed. Only the direction is changed. Whenever a charged particle experiences a force in a magnetic field, it experiences force and it changes direction, but doesn't change the magnitude of the speed. So it moves in the circular path, centripetal acceleration. Okay, so if it moves parallel to the field or anti-parallel to the field, sine 180 or sine 0 gives 0 answer, no force. That means path is a straight line. Perpendicular to the charged particle moving perpendicular to the magnetic field, circular path. Neither perpendicular nor parallel, then it is helical, you know. If the charged particle is moving like this, in this direction, then you can split this velocity into two components. One is, so if this is theta, one is v sine theta, another is v cos theta, and v cos theta takes it along the direction of the magnetic field. V sine theta makes it to move in the circular path. So one velocity makes it to move in the circular path, another takes it forward, so that becomes a spiral. So that is another part of this force. So force acting on a charged particle is QEB sine theta. Now if you take a conductor, a straight conductor, and keep it in a magnetic field. This is the magnetic field shown by parallel lines like this, and if a conductor itself of length L carrying current I is placed in a magnetic field making an angle theta, then what is the force acting on this? Of course, there is a small derivation for it. You have to look into that. I don't go for all the methods. So force acting on this, finally we get, it's because you have to differentiate this, and finally you will get BIL sine theta. Or if you want to put it in the vector form, F is equal to I into L cross B. I into L cross B. ILB sine theta. L cross B is LB sine theta. So I into L cross B. So any conductor placed in a magnetic field making an angle theta with the direction of the magnetic field experiences a force. Again, it is given by Fleming's left hand rule. Only the change that you have to do is here, instead of direction of motion of charge, you have to take it as current. Because here so many charges will be moving and they will be producing current. So if the forefinger represents the direction of magnetic field and middle finger represents the direction of current, motion of positive charge, then thumb shows the direction of force, of course. That is another formula. And then came the magnetic field due to a circular coil carrying current. Current loop, very, very important derivation using Biot-Savart's law. So a circular loop was taken like this, and you know how to find out the magnetic field due to a circular loop. If there is a circular loop, magnetic field can be taken like this. You can use the clasp rule in the reverse way for a loop only. If the current is like this, hold the fingers in the direction of current, whereas to find out the magnetic field due to a conductor, we use fingers to represent direction of magnetic field and thumb current. Here, the thumb represents the magnetic field and fingers represent the current. So it is like this, then it is into the board. And if the current is in the anti-clockwise direction, like this, out of the board, out of the board like this. So any current carrying loop produces a magnetic field. And what is the magnetic field at any point? You remember two elements were taken here, this is joined, and the magnetic field due to this element here is dB like this, right? You can apply Fleming's Bayer-Savart's law and get the magnetic field here, and it is perpendicular to the line joining the plane containing the element and the line joining the element with the point, and it will be like this. We have done all the circles to find it out, and you draw a perpendicular here like this, and if this is alpha, then dB cos alpha, dB sin alpha, something like this we have found out. And again another element taken here, and its magnetic field will be like this. This is also alpha. Again this can be split into dB sin alpha, or dB perpendicular and dB parallel, right? dB cos alpha. Then we have added this 2 dB cos alpha. Cos alpha can be taken from this triangle. This is radius, this is x, and all. Just refresh it once, right? If you have any doubt, you can ask later through WhatsApp. But refresh it, otherwise it becomes difficult. Okay, what is the magnetic field at this point now? Magnetic field at that point is mu naught Ni by 2 into r square plus x square to the power 3 by 2. So magnetic field due to any straight current carrying conductor, magnetic field due to any circular coil carrying current, that is what you call current loop, along its axis at a distance x from the center of the coil is mu naught Ni by 2 into r square plus x square to the power 3 by 2, where mu naught Ni r square, right? Mu naught Ni r square divided by 2 into r square plus x square to the power 3 by 2, where n is the number of turns in the coil. Of course, we are not using this in derivation. Mu naught I r squared. I is the current through the circular coil, r is the radius of the coil, and x is the distance from the center to the point where we are measuring the magnetic field. Now, where will be the magnetic field maximum? At the center. How to find it out? Magnetic field at the center of the coil will be maximum, and that is possible if x equals 0. If x equals 0, what you will get? This is 2 gets cancelled, r cube. You get magnetic field at the center of the coil, mu naught I by 2r, isn't it? Mu naught I by 2r. So r squared, x will be 0, r squared to the power 3 by 2 is r cube. 1 r gets cancelled, mu naught, and if you want you can take n number of turns. So magnetic field at the center of the coil is mu naught Ni by 2r. That is also over. Then we, as if we had Gauss law in electrostatics, we have Gauss law, not Gauss law, Gauss law in electrostatics. We had another law, Ampere's circular law, which says the closed integral of B dot dl is equal to mu naught times the net current enclosed by the area under the curve, right? So try to remember it. It is also needed in future. So if you have a straight current carrying conductor, infinitely long, say, infinitely long straight current carrying conductor. It is very long. Only I am focusing on this part, that's all. It is very, very long. I want to find out what is the magnetic field here. How much? A straight current carrying conductor will produce magnetic field around it. And you can obtain it by clasp rule, and it will be like this. It will be encircling the conductor like this. So if the current is like this, so you have to clasp it with right hand. Now what is the value of it? Of course, here I have changed the conductor direction like this, so it carries a current like this, I, like this. What is the magnetic field here? So according to Ampere's circular law, closed integral, line integral of B dot dl is equal to mu naught times the net current enclosed in the area bounded by the curve in the closed loop. What do you mean by that? What you have to do is, around the conductor at the same distance r, you imagine a loop like this. Imagine a loop, so that conductor passes through the loop. A circular loop is a better choice here. So when you imagine a circular loop around the current carrying conductor with the radius such that you reach to the point, or this point is the part of that ring or the circular loop, then this says you take a part of the loop like this, B dot dl. How will be the magnetic field? It is in the direction of the loop itself, because you know that in a current carrying conductor, the magnetic field is in a circular loop. So we have considered ampere loop in the same way. So the direction of magnetic field and the direction of the loop are in the same direction. So if you go for B dot dl, then B dl cos theta, you know that A dot B is AB cos theta, theta becomes 0. The magnetic field direction around the circular coil and the loop that we have considered, both are identical. So the direction is same for both. So theta, they overlap on each other. So theta is 0. So what is the closed integral of B dot dl? You have to go for B dot dl, B dot dl, B dl cos theta. When you go for this, every time cos theta is cos 0, 1. And every time B is same. When the conductor carrying current is like this and the circular loop is like this. Everywhere the distance is same and current is same and magnetic field is same. And the direction is same as the circular loop. So when you integrate this and complete the closed path, what you will get is the total dl, that is what you get. B is a constant. Everywhere B is a constant. Cos theta is a constant. Cos 0, cos 0, cos 0, cos 0. Only integration of dl. That comes to, so the left hand side becomes B cos 0 and dl becomes 2 pi r. 2 pi r. dl, 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 dl plus. You complete the circumference then is equal to mu naught times the net current enclosed by the area under the curve. This area of the curve encloses only this current I, nothing else. So total current enclosed by the area under the curve is mu naught I. Then what you will get? So B, magnetic field due to a straight conductor carrying current, is mu naught by 2 pi I by r. This is the magnetic field due to 2 pi r. I have written mu naught I. So this is important formula at least, and statement of this Ampere's circular law and its application. This is one of the application. Mu naught by 2 pi I by r. Of course, if you want for entrance exams, of course here it is mu naught by 2 pi I by r. I can write it as mu naught by 4 pi 2 I by r. Right? Then what is the magnetic field at the edge? Mu naught by 4 pi I by r. Half that at this. Mu naught by 4 pi I by r. This is how we have to do. Okay? So that is the thing here once. Okay. Then we applied Ampere's circular law to two more things. One is a solenoid and a toroid. So what is a solenoid and what is a toroid? Okay, we will move on to solenoid and toroid. Solenoid is a long wire wound on a small tube, a very long tube but very small in diameter, so that each turn is parallel to the previous turn, very close. So this is solenoid, like this. This is a solenoid and the two ends are like this. And if it is very long, of course, it is called ideal solenoid, very long solenoid. Then what is the magnetic field inside a solenoid? And you can apply the Ampere's circular law again and to get the magnetic field at the center of a solenoid. What you have to do is, the solenoid has to be taken, of course, Ampere's circular law, closed integral of B dot dl is equal to mu naught times the total current enclosed in the area within the curve or loop. So you cut the solenoid. So solenoid was like this, but it should be infinitely long. Cut the solenoid like this, like this. So what you will get? You will get a structure like this, half piece of the solenoid. Then of course the windings are coming out of the board, say here. They are carrying current like this, say. They are carrying current into the board like this. Suppose they are carrying current out of the board here, into the board here. All these coils taking out of the current here into the current, into the board. This is the axis of the solenoid. And you know that every wire is coming like this. And the magnetic field, suppose you take the two adjacent wires like this. This wire is coming out like this, carrying current like this out. So it is like this. This wire will be producing magnetic field like this, correct? What about the previous wire? It will also be carrying current like this outside. As you move, so this part of the wire is carrying current like this and it is moving forward and coming out on the other end. So here also it is coming out. So how will be the clasp rule? So it will be producing the magnetic, so coil is like this, it is coming out. So it will be producing the magnetic field like this. in the same way, but by the time it reaches here, the magnetic field vanishes, because the magnetic field due to this part of the wire is like this. This part of the wire is like this. Apply the class pro. Here it is like this. Here it is like this. Here coming in. They cancel each other. No magnetic field is found on the surface of the coil, and no magnetic field is found outside because it is too far away. Magnetic field inside will add up. See, this magnetic field is like this, and it is like this here. What about this one? Like this here. Here they cancel. What about here? They add up. See, here they add up. So there is a magnetic field like this. Magnetic field inside the coil is particularly directed in one direction. In order to apply Ampere's circuital law, you have to assume an Amperian loop. I don't have color chalk here. I need one color chalk. Yeah, you need an Amperian loop here. You have got the color chalk, so now you have to apply Amperian loop. I will consider an Amperian loop of length h. You know that n is the number of turns in the solenoid over a length L. Then I call it by small n. What is small n? Small n is the number of turns per unit length, per 1 meter length, or 1 centimeter length, per unit length, some unit. So number of turns per unit length is small n. If n is the number of turns in unit length, what is the number of turns in h length? nh, correct? Over a length L, it is n. What is about over a length h? nh, the small nh. Okay. So now, what you have to apply the Amperian loop, Ampere's circuital law. Start from here, move like this. Now what happens is, you are moving along the magnetic field now, correct? In the direction of magnetic field. So closed integral of b dot delta L, b dl cos theta. We get cos theta cos 0. Cos 0 is 1. This is 0, because you are moving along the direction of the magnetic field and the Ampere loop. I am moving from A to B, C, D, say. So as you move, cos 0 is 1. dl is this h. And b into h, I have moved through a distance h, right? b into h, cos 0, 1 plus, you have to complete the Amperian loop because it is a closed integral. What about here? As you move like this, the current is perpendicular to the, if you go for BDL, magnetic field is like this, and the loop, a part of the loop DL is perpendicular to it. Current, magnetic field is in this direction, but the loop is like this. BDL cos theta, cos 90, 0. No magnetic, no Amperian loop here. Or Ampere's circuital law can be applied here. What about this way? No B at all. There is no magnetic field outside the solenoid. No B. What about here? Again the same condition. When you are moving perpendicular, when the magnetic field is perpendicular and the loop is, DL is perpendicular to it, BDL cos 0, 0. Cos 90, sorry. BDL cos 90, 0. So 0 is equal to, understood? As you move from, you have to complete the Amperian loop and make B dot DL, as if we did in a circle last case. BDL, when you go for this one, you can have the small elements, DL added, H, B into H, that is B. But here, B is like this, but DL is perpendicular, cos 90, 0. Here no magnetic field at all, B is 0. Here again perpendicular, so 0, 0, and only this remains, mu naught times the net current enclosed by the area under the curve. How much current passes through this? So how many turns will carry the current? One current, 1I. Another wire, 2I, 3I, 4I, 6I, all the current, mu naught times the net current enclosed by the area under the curve. In the last case, we had only one wire, so one loop, so only I. Here so many I's. How many I's? N windings are found in 1 meter. What about in H meter? NHI, correct? Did you understand? 1 meter contains N number of turns. H distance contains NH number of turns. So NHI, BH is equal to mu naught NHI, and HH gets cancelled. B is equal to mu naught NI. So magnetic field inside is solenoid is a very long solenoid, it should be mu naught Ni. Okay, that is one application. Okay, the second application of Ampere's circuital law. The third application of Ampere's circuital law, that is toroid. What is a toroid? Toroid is a long solenoid made into a tube like this, right? Circular tube, and it will have Yeah, it is a toroid and the wire has to be wound over it like this, correct? Yes. And here are the two ends of the coil like this. It has started winding like this and has come out. What is the magnetic field at the center here? It is 0. What is the magnetic field outside? 0. Because you know, if you open it and make it a solenoid like this, you know that magnetic field here and here are zeros. Only magnetic field is found inside the solenoid, right? So there is a magnetic field inside only, here only. No magnetic field here, no magnetic field here. You can prove it using Ampere circuit law. Now you have to consider an Amperean loop. What is an Amperean loop? A loop which encloses the current carrying conductors. Whereas in Gauss theorem, Gauss law, a surface which encloses the charges, closed surface, maybe sphere, cylinder, you may be remembering it. Okay, now you consider the Amperean loop like this. We will consider one more colored chalk I want. I'll bring it, it is here. Yeah, I have pink color. Yes. Now, if you consider an Amperean loop here, with this point covering here, what happens? This part of the formula becomes 0. Why? Because as many number of turns take the current out, same number of currents go in. So if this is the Amperean loop, net current, you see the meaning of this, net current enclosed by the area within the loop, net current is 0. Because as many currents are coming out, same number of currents are going in, plus I, same amount of minus I. So the outside loop, if you consider a point here and a ring covering that point as an Amperean loop, then it doesn't cover any current. So right hand side will be 0. If right hand side is 0, then B is 0, right? Because the Ampere loop has a length. Length is not 0, so B should be 0. Now consider a point inside. Inside means here. Consider a point here, right? This doesn't enclose any current at all, this Amperean loop. Suppose I want to find out that there is a magnetic field here. Using that point, draw an Amperean loop. That doesn't enclose any current carrying wires. All the current carrying wires are here. So what is I? Again I 0. That means B is 0. Now enclose a point here. Suppose this is a toroid of radius r. Now imagine a circular Amperean loop inside the toroid of radius r. If I want to find out the magnetic field here, there should be a magnetic field there. Now how to find it out? Now here you see this Amperean loop doesn't enclose these say going into or coming out wires, and they are going in here, taking the current inside. Say current is taken out and going in, taken out, going in. So like this. This Amperean loop, marked purple color, is enclosing only these wires. So if n is the number of turns per unit length, then how do you write the Amperean loop? This closed integral of B dot dl. After going for closed integral of B dot dl, B is a constant because B here, B here, B here, B here should be same because they are at equal distances from the center. Magnetic field at all the points should be almost uniform. So B dl becomes 2 pi r cos theta. What is cos theta? Cos theta is, you see, magnetic field is along the wire like this and you are moving along the direction itself, right, in the same direction. Magnetic field is along the axis and Amperean loop is also along the axis. Cos 0 must be equal to mu naught times the net current in the area bounded by the curve. This purple curve, Amperean loop, bounds how much current? If n is the number of turns per unit length in the toroid, what about the total number of turns and total current passing through? How many times the same current encloses inside? So it is enclosed inside. So how many times means it is 1 meter contains n turns. 2 pi r meter contains how much turns? Right? N into 2 pi r times the total current, because one turn carries 1i, 2i, 3i. How many turns are there? N turns in 1 meter, 2 pi r turns, 1 meter contains n turns, number of turns per meter. 1 meter contains n turns, 2 pi r meter contains how much turn? So n into 2 pi r I, 2 pi r gets cancelled, magnetic field inside the toroid is also mu naught I. So these things we have finished, correct? I hope so. Next we have to go for some other things in this chapter also. Okay, that we will do in the next class. For the timing, I'll stop it. So try to remember all these formulas, starting from Biot-Savart's law, force on a charged particle moving in a magnetic field, F is equal to q v sine theta. Biot-Savart's law, mu naught by 4 pi, ideal sine theta by r squared. Force on a conductor carrying current, F equal to BIL sine theta. And what else? Yeah, magnetic field due to a circular coil, mu naught Ni r squared by 2 into r squared plus x squared to the power 3 by 2. Mu naught magnetic field at the center, mu naught Ni by 2r. Then magnetic field due to a straight current carrying conductor. Application of this, that is mu naught by 4 pi 2I by d, or mu naught by 2 pi I by r. Then solenoid toroid, mu naught Ni. So with all these things, open the book once. I think you might have been having that book what you have written in the class, and that notes what you have. Open it once, see what are the things covered. Come prepared for the next class. We will have that very important derivation, that is force between two straight parallel conductors carrying current. That is very, very important. Thank you for watching, and we will meet in the next class.